So thank you very much for the kind invitation, Anna, Viesha, and Zara. And I was there when the whole procedure of the conference was decided, because I was in the scientific committee. So I'm really glad that it takes place. I'm, of course, very saddened that Jan died. People will always die very early. So I'm going to present a new, completely new approach of problems we have been thinking about for quite a number of years, notably with Michael Groechenig. And it just so happens that now we have a method which enables us to say more than what we could say before. And in addition, which is purely local in the sense that it's local over the width of the width vectors and doesn't appeal to complex geometry. So it is quite likely that it will yield a new understanding of a few problems around the problems here I've been thinking about for quite a number of years. So I have my notes here, and since I'm completely jet-lagged, I hope you allow me to look at the notes to lecture. So let me first make some. So the plan of the lecture is like this. I will just give the theorem. So I need the assumption and the theorem. Then I will explain the terms in the theorem, because we have quite a broad conference here, which reflects a little bit the area of expertise of Anna, Viesha, and Zara. So we are not all in the same topic, technically speaking. So I will explain the terms, and once I've explained the term, I will explain what was before available and what it gives new. And then I will say a few words on the proof, the new idea of the proof. So first, let me start with the assumptions, because I will use this terminology all along. So we have X, so W is a W of a finite field of characteristic P, and all along we will assume P at least 3, and I will explain why. And X here is smooth over W, and it is endowed with a good compactification. Good compactification means with a relative, so it is smooth over the base, and it has a relative normal divisor at infinity with normal crossings. And then we pose a definition. EW, it's going to be a vector bundle of rank R, and which is endowed with a logarithmic. So I denote by W the complement here, and it's the notation nabla W is going to be a connection here with logarithmic poles, which is integrable. So maybe I put a bar here to indicate that we are over the compactification. And then we say that it has unipotent monodromies at infinity. As usual, this is just meaning that the residues along the branches of D of nabla, so maybe I put a bar here, are nilpotent. So that's shorthand for a classical notion here. So this is equivalent to saying that the eigenvalues are all 0. And then this is the first piece of definition. The second piece of definition is to say what it is rigid. And rigid means that it cannot move along a one-parameter deformation, keeping the conditions at infinity. So this is also with respect to conditions at infinity. And the third piece of definition here is that this is, we translate this rigidity here with a more geometric notion by introducing a moduli functor, which I denote by M de Ram, which takes into account those vector bundles here, so that's connection on locally free shifts, together with the condition at infinity here. And they exist by the work of Langer. so over W. And because our residue field here is C1 in the sense of Emil Artin, in fact, and of Lang later on, this has a property that if we look at the W points here, this corresponds really to objects as before. Okay, so this is a very classical thing. And in addition, so those are these are moduli of stable objects in the sense of Mumford. And on the generic fiber, it means that the connection is irreducible. So in not IE, but in particular. So irreducible on the generic fiber. Capital K is going to be the field of fractions here. And then it is a case that if we look at the W points here, and of course we can restrict those W points to capital K points. And then it is a case that any capital K points here, so let me write W here, it's an isomorphism. So that's a capital K points which extends as W points here. Bijection, right now there is no... and then the rigidity means that it's a zero dimension, so rigid over capital K, it's equivalent to zero-dimensional components. That's a K point is a K point in a zero-dimensional component.
I think you said, but just to check, is the divisor at infinity is flat over W?
Relative normal crossing divisor.
But does it can have components in characteristic P too?
No, flat. Thank you very much for asking. Yeah. Thank you very much for asking. Okay, so now let me formulate the theorem. There are two theorems, 1 and 2. So we are in the assumptions are as before. And then the first theorem says that if we look at, if we assume that E bar is rigid, then it will be the case that if we look at the formal completion of the connection, so let me write, I'm sorry, it's a little bit of a heavy notation, but I don't have a shorthand here. So on the formal scheme, then this one, which is a connection here, well, in fact, let me remove this. On the open here, because otherwise I have to explain even more. On the open, this represents an F-isocrystal. So underlies the structure of an F-isocrystal. So that's the first part of the theorem. Now the second part of the theorem is an enhancement of this. The second part of the theorem, if we assume in addition that P is more than the rank of E, so if in addition P is more than the rank of R, maybe I didn't introduce R before, and every rigid connection, every E bar, nabla bar as before, under the assumption, in the given rank, has the property that it admits the filtration. Let's say a Griffiths filtration, Griffiths transverse filtration. Let me write it fill with two properties such that the first property is that it's locally split, so it's transverse and it's locally split. And the second property is that the induced Higgs bundle, the induced linear operator Groe-Nabla bar on Groe I bar. Let me write here infinity for simplicity. So the induced linear operator is stable in the sense of Mumford. Then the conclusion is that this Griffiths filtration induces on the formal object a structure of a Fontaine-Laffaille, let's say, Faltings module.
So to define what is stable, do you have to fix a polarization?
I cannot hear.
To define what is stable, do you have to fix a polarization?
Yeah, so the scheme before the good compactification, thank you for reminding me, is projective here. Thank you very much.
And you use the Mumford or the Giesecke stability?
This is a slope stability.
Slope stability.
But I'm not going to enter into the details, but thank you for asking.
So the existence of this filtration is an assumption, or is it conclusion?
It's an assumption. If in addition you have this, then you have this. Now, I will not enter into the details because I want to present to you a new proof. I want to say how it relates to all your work, and then I want to say what is the motivation, and then I want to say what is new in the proof. But at any rate, I can say already, because it was asked here, the moment you have a Fontaine-Laffaille Faltings module, you associate to it in a way which is Foley phase fall. You associate to it a Q adic representation, local system on the algebraic X over capital K, which has a crystalline property. But I will not enter into this. That means you will have as many crystalline local system on the algebraic fiber over capital K as many as rigid local system you have in your moduli space, which are defined over capital K. So
plus the filtration, right? You have to
under this assumption, of course. But okay, but I want to give the motivation a little bit later, and then I want to tell you that this assumption is always fulfilled when you come from complex geometry. But here I wanted to present a purely local theorem which has absolutely nothing to do with transcendental methods. So let me explain. So now I just, because as I said, we are quite diverse, so let me explain the concepts here in the theorem. So the first one is isocrystal. In fact, of course, it's a notion which is on the mod P reduction of the variety. It's a vector bundle. It's a locally free module in a specific side, which is called the crystalline side. So this is the old This is one way of thinking, and another way of thinking is precisely this, this formulation here on the open variety. But concretely, on this algebraic version here, this is equivalent to saying that the P curvature of the mod P reduction of the connection is zero, is nilpotent, I apologize. So that's equivalent to saying that it's an isocrystal, and now Frobenius, the Frobenius structure on this isocrystal, there is one way to think, which is, for me, the easiest one, is that because P is at least 3, and the base is unramified, we are over the width of over W here, then it is a case that if we take local lifts of the Frobenius on X bar over W, and the question of math here makes a lot of sense because we need smoothness here. Then so we take those local lifts, then we can pull back the connection along these local lifts locally. So the formal connection. So this exists, and then because P is at least 3, you can compute by yourself that as you change the local lift here, this object is isomorphic. If we have 2 lifts, then we have an isomorphism, which is a canonical isomorphism, which produces a co-cycle, so the Frobenius lift is well defined. And then to say that our object has a Frobenius structure is saying that in fact it will be even stronger because it will be also on the compactification, but it's saying it's well defined, so I denote it just by F upper star, and then it's saying that the power of F upper star stabilizes the object. So there is an N such that the Frobenius pullback here is isomorphic to itself. Okay, so that's here I made a mistake here. This is on the completion here. Okay, so that explains the first theorem, and now as for the second theorem, we need a slightly more complicated concept. We introduce the second theorem. We will need the notion of a flow. I mean, it's a sort of an easier way to think of the concept of Fontaine-Laffaille and faultings. But in order to do that, I first have to introduce this notation here is due to Nick Katz, Mick. So that module is an integrable connection, except that our modules here are really locally free from the very beginning, so that I don't repeat again. This, and then we can so look at our scheme here. So those are the locally free. Those are precisely the objects like in the assumption. And then we put all morphism which respects the connections. And then inside, we can look at the subcategory of those objects which have the property that the mod P reduction has 0 P curvature. So then this is one piece of notation. The second piece of notation here is that we can look at the P connections. I'm sorry, it's a bit technical, but later on it won't be technical at all, but I have to introduce this. So that, and also 0. So let me introduce first the P here. The P stands for P connection. And what is a p-connection? It is just, I think the terminology essentially originates in the work of Deligne, which follows the work of Simpson, that he had this idea that the Higgs object comes as a specialization along the lambda line of a connection. So you have to introduce the notion of a lambda connection. So this is a p-connection here. And a p-connection here is just that when you look at the Leibniz rule here, so if S is a section of your bundle and lambda is a function, a regular function, then it has to be p times d lambda S plus lambda nabla S. And the 0 here, so when you have a p connection and you look at mod p, then the mod p is it's a connection with p equals 0, mod p. So that means it is a Higgs bundle. And the 0 here refers to 0 Higgs bundles of the mod p reduction. The same way here, the 0 here was referring to 0 p curvature. So that's the second piece of notation. So by the very definition, if you think a little bit of it, if you take mic, and then you multiply your connection by p, then it's going to be the same as this pic mic. Okay, so this is just a tiny bit of notation here. But why do we introduce this notation? Because we have on it, we have the so-called Cartier inverse functor.
Do you have 0 on the left-hand side too?
No.
Because you put, and that's because you put 0 on the right-hand side.
No, no, here there is no 0.
But there is a 0.
But here there is 0. This one, this time it was okay. Thank you. So you have the so-called Cartier inverse functor, and the Cartier inverse functor, it goes precisely from this category, or if you like, equivalently from this category. I mean, I'm sorry, I have to follow a little bit the history. Maybe we can simplify the notation here. So the Cartier inverse functor. And the Cartier inverse functor goes to, now this one with 0, in a way it goes the opposite way. And so here, because of what I have written here, I can certainly first inverse P. So I'm here, now I'm mic, but with no condition on the mod P reduction. And then we can, because of what I have explained before here, I forgot to say that this computation here is true by Berthelot on the smooth part, and for the log poles, it respects the unipotency condition. So you have to compute it. And the way to compute it is to take a local Frobenius which respects the divisor at infinity. So I don't do that. So here you can put Frobenius inverse. So that's the Cartier inverse functor. And then the theorem here on this one. So I'm still explaining the main theorem here, but I have to explain the concepts here. And the theorem which is in the shadow here, the first part of which, the main part of which is due to Shu on the open part, is that C inverse is an equivalence. It's an equivalence of category, and it lifts Cartier inverse functor on the mod P reduction, which is due to Gauss and Vologodsky. And then you can also compute what it does with poles at infinity. Then with poles at infinity, the inverse is not exactly an equivalence of category, but it is still fully faithful. So it is an equivalence to its image, its essential image here, and the essential image here are those which, so the unipotent objects here with the property that the P, that the residues, so are not only nilpotent, but they are P divisible. So once I have said that, I have to explain what is a flow. I announced already that there is a flow, and then once I have explained the flow, I will have explained what is here. The flow, which is denoted by phi, capital Phi. So now, for this, we have to do the so-called Artin-Ries construction. Which at least I learned this from Faltings, from his work. So we first introduce the MIC endowed with a Griffiths, the category of MIC endowed with a Griffiths filtration, which I denote by F-MIC. So again, same notation here. So then the objects are just field and the enabler. Where so again, so they are always unipotent at infinity, vector bundles, etc. This one is Griffiths transverse, like in the theorem here. And so the Groe is locally free. And now, out of that, we can construct a new lattice, which is what Faltings does. So you can associate to this. Let me call it simply Artin-Ries, but I will not write it as an Artin-Ries exactly. In the P-MIC, I'm sorry. I'm really jet lag, I apologize. So to one such object here, you associate here the object which is field E P minus I, where I now, and from it, you look at the O module. And all this inside of E bar hat, tensor capital K. And if you, so for example, if you had only one step in the filtration, so just field 0 and nothing else, then you would not do anything. But for example, if you have, like in a family of curves, if you have field 0 contains field 1, then you change the lattice here. On field 1, you replace field 1 by field 1 divided by P, and then you keep field 0. That gives you a new vector bundle. And now it's no longer the case that this new lattice is respected by the connection, but it is the case that if you multiply this connection by P, it is respected by it. So this is P nabla compatible. And for this reason, you obtain a P connection here.
So what is the meaning of OXW bar?
You take the sum module spanned by those. For example, if you have only E1, E2, E1 is F1 and E2 is E0, E1, I apologize. E1 is F1 and E0, E1 is a whole F0. Then you change the lattice by taking E0 and E1 over P. This is what I said. So, so now comes the beauty here, which starts with Shiro. So it's a reinterpretation of Fontaine-Laffaille Faltings. I mean, not completely reinterpretation. So we do as before. Locally, we have a Frobenius lift. which I denote like this. So locally, you can define phi to be the Frobenius pullback, and then precomposed by the Artin-Ries construction divided by 1 over p. That means, if you like, you apply the Frobenius leaf to the F mic, and that means to mic. And then it turns out that Faltings gives a gluing, which is a highly non-trivial gluing of those local expressions. And this defines the functor phi from mic, the Frobenius mic. Oh, shit. To mic. Respecting the unipotency. That's a proposition of Faltings. And it is a case, so you have a proposition here, which you can compute, and this is due essentially to Shu and Leng Sheng Suo. That if you look at the mod P reduction, then this corresponds to the, I just write, this is the August-Vologodsky correspondence. And in particular, it preserves the stability conditions. Okay, so I think it's enough technical thing. And that is true the moment we have August-Vologodsky, so that means we have to assume that the rank, that the P is more than the rank here.
But August-Vologodsky doesn't see the filtration. Do they see the filtration?
Oh, no. If you look at, I don't want to, thank you for the question. When you look at it, what it does here, you have a filtration that gives you graded objects, that gives you a Higgs, and then that corresponds, this corresponds to the Cartier. Okay.
And in Frobenius mic, I don't see on the blackboard, but is there a condition of divisibility by Frobenius? In the definition of Frobenius mic, you have a filtration, a bundle, and connection, but is there an action of Frobenius also?
On
F mic.
That's a Frobenius. I'm sorry, I cannot hear what you say.
In F mic, is there also some Frobenius?
No, F mic is just the category I said before.
There is F is not Frobenius.
Yeah, no, F stands for filtration. Yeah, maybe, thank you for, I apologize there. And now I can say what it means. Now I can say definition. And then I'm done with the technical part. I can say definition is that a Fontaine-Laffaille module translated in the way Leng Suo. So Fontaine-Laffaille and maybe Faltings module. Translating with Shu Sheng Suo. It's not so far from the original language, but it's more convenient to see it like this. Is that phi, an object is a Fontaine-Laffaille module if it is phi stable for some power of phi. So there is this an n, such that phi n opposed star of the field in Abla, and then with the decoration here, is itself. So the theorem here, so that is called the Higgs-Durham flow. So if you like terminology, the phi is called the Higgs-Durham flow in the literature. So in characteristic P, it is really Higgs to Durham. And, but in characteristic 0, the moment you are over W, then it mixes the two notions. Nonetheless, it is called the Higgs-Durham flow. So now, if we come back to our theorem here, so that was the definition. So the theorem is here. If we come back to our theorem here, here we ask for a Frobenius fixed point under the assumptions we have, that we have a rigid point with a unipotent rigid point, which is locally free. And here we ask for a Higgs-Durham flow fixed point. That's so it looks like it's a similar problem, and there is only one proof for the two. Yeah, Matt?
The way you wrote it, phi lands in a different place to where it starts.
Yes.
So how do you do it to the nth power?
Thank you very much. So thank you for asking. I thought I could shorten, but I cannot. So let me explain this. Is that okay if I write here? Can you see?
I can. It's great for me.
Okay. So it says like this. Thank you, Matt, for the question. I was too fast. So you start with your inabla. And I'm going to explain to you what it means that it is fixed. Now, by the assumption here, I should have recalled that, it is endowed with a filtration. So now I can take the phi of that. The phi is going to be, of course I have to prove it, that it's going to be a new object of this kind. But only an inabla of this kind. So let me write here 1, W1, and then nabla bar hat W2, 1. A new one, I call it 1. This one I call 0. This one I call 1. But it's going to be of the same kind, because I said it preserves everything. So, well, here I didn't say that it preserves the isolated point. It's going to come. And it's going to come in the proof. So this is, again, by our assumption, endowed with a field. And then I can keep going, and then it is stabilized here. So thank you for the question. So the field here was part of our assumption. So in this theorem here, it's the phi, I apologize. The field, yeah. What is written here contains two information. The field was part of the assumption, but it contains first fact is that the phi is going to stabilize the rigid points with unipotent monodromy at infinity, and second point, it's going to be cyclic, to be periodic. Is that okay? So thank you for the question. It was an important question.
Do you say that the filtration is defined using the old one, the filtration on phi?
It's part of the assumption. I'm not saying in the nature you take any rigid point over W, then there is a filtration. This was a question of Yesha. But I have an assumption here, and I take this assumption.
No, but after you apply phi, you have a filtration on what you get?
No, I'm not claiming this. Phi doesn't give a filtration, but my assumption contains a filtration on all such objects.
So this is some additional choice of data.
It's written in addition. Once again, so maybe it wasn't clear, and I apologize if it wasn't clear. Phi is a functor which assigns to field inabla with all the decoration a new inabla. Now, if I prove that phi, in particular, keeps the finite set of zero-dimensional components of my moduli, the new inabla by this additional assumption will be endowed with a field. So I can iterate the phi. And then it makes sense to say that I have a fixed point. No, Offer, your question is not legitimate, if I may say so. It is written, I assume that I take this one. I take one filtration.
But somehow in the end, you'll control it in some way.
Yeah, I control. In fact, if you come from complex geometry, it will be. There will be a canonical field. But here the formulation is just we assume it exists and we endo with this one. And then with this one, I tell you this is true. And in fact, if I had taken, if by accident there were two, you can always ask the question because certainly Offer wants to ask such a question, then at the end it would still be cyclic like this. Is that okay? So thank you for the questions. So I think I explain the theorem, and now let me explain the yeah. So now let me make two remarks here before I proceed on the history here. So first a remark, the motivation, and second, what was available, and then I go into the quite a new way of thinking. Is that okay? So first the history, all that relies on a very, very deep conjecture. I mean, not rely concretely, technically, but the idea to look at that on a conjecture due to Simpson, which says that if X now was over C, and I don't give all the, again, you fix infinity, blah, blah, then rigid connections are of geometric origin. So now if you believe that it's really of geometric origin, if you go to P very large, you take a model of your all blah blah, and then you take P very large, so it will be unramified, etc. Then because the morphism of which it is coming from is going to be smooth for P very large, it will be the case that you will obtain, in particular, a P adic local system which is crystalline. So the underlying crystal object, first it should be an isocrystal, that would be theorem 1, and theorem 2, the underlying crystal object should have this Fontaine-Laffaille property. So that is why you look at that. And in fact, and now so that's number 1. And now the theorem 1 for X proper, and then again, Offer is going to ask projective because we do modular functors. In fact, in the article, we don't do modular functors because, of course, Michael is way younger than me, so he does stacks, so you don't need that. But in my presentation here, I have a projective. So it is a projective here. And then we had theorem 1. Like 4 or 5 years ago, it's published in ACTA with Michael, so I don't repeat. We had theorem 1, not for all P's which show up here, because I was saying you start with characteristic 0, your connection is going to be over W for an open of P, so to speak, to say loosely, but for infinitely many P's. So it's a substantial improvement because here it gives you all P's in an open of definition, but even more, it takes you exactly where possibly it could fail. And the second theorem here, again with Michael, and I will make a comment on one again, but let me finish here. The second theorem, which is more subtle, I mean, which goes deeper in the theory because it ultimately it will give you a crystalline local system. I don't write it here. I stay on the Durham side. Then this second point here was proven again with Michael as an appendix to the article of Pila, Shankar. So I always forget whether this is an H and Zimmerman proving the André-Oort conjecture for Chimois varieties of real rank at least 2. Here we could really prove that we have an open of P's which do exactly what is written here, but under a much stronger assumption. Not only the connections were rigid, but they were strongly cohomology rigid. So it shows we don't need that. Strongly cohomology rigid. So first, let me explain what is cohomologically rigid. You have a point of a moduli space, and it's isolated. It's a zero-dimensional component. So there are 2 options. This zero-dimensional component is a smooth point, or it is a point with multiplicity. So if it is a smooth point, it's called cohomologically rigid. And why the terminology is because the tangent space of your moduli is given by a cohomology. That's H1 with decoration at infinity, because we fix infinity of the endomorphism of the object. So this one should be 0. And then strongly cohomology rigid means the same thing, that you look not only at the moduli with boundary conditions, but you look at the moduli without any boundary condition, and then you request that the point there, its Zariski tangent space is 0. And that happens for Chimois varieties of real rank at least 2. And the last remark before I enter here, bis, is that in the lecture notes I wrote following the Eilenberg lectures I gave last fall at Columbia University. So lecture notes, which just appeared like a few days ago. Springer lecture notes, chapter 8. Then I give the first proof on which I had talked with Johan de Jong. I gave the first proof of the theorem 1 here, not going modulo P. And I should have said here, this proof here was going modulo P square, etc. This is the first p-adic proof here, local proof, if you like, which is using the first thing I mentioned here. So we are in the proper case here. And it's using the first theorems I mentioned, is that the Frobenius is defined on connection, under the assumption that the residual characteristic is at least 3. So it was given in characteristic at least 3 under this assumption, but using the properness strongly, and using the so-called formality of the moduli of connections, a notion which had been a theorem which had been conjectured by Deligne in the 80s and proved by Goldman-Minson, that you can describe the formal local ring of the moduli space of connections by using cohomology. And I don't say how, but so we were using cohomology here. Okay, so I think I didn't forget anything. And now I have like 6 minutes. No, but there was an introduction, so maybe you give me 1 more minute and oh, then it's more than I can say, so it's okay, thank you. So the new tool we use is a topology on M de Ram W. So of course M de Ram, as I said, there is one thing I forgot to say here in the history, that the way it is written in our article, again, so we can get rid, using stacks, we can get rid of the condition unipotent at infinity and replacing it by quasi-unipotent at infinity. It adds quite a difficult technical technicality in addition, and I don't talk on this. And also I'm less home than here, I don't have to think. So this topology on MW. So this is a scheme which is defined over W, as you remember. So then there is on any scheme of finite type and also on stacks, but we don't talk on this. There is a so-called strong topology. And this strong topology had been worked out, as I understood, first by Morebelli. And then in all generality by Cessna-Vicius. And it says basically on schemes, here this is more complicated in the talk, we don't need this. It says the following: when you have at least a scheme of finite type, then you have to know that, so you have to know two things to define the topology. The first thing is that it's compatible with Zariski open. So if you take a Zariski open inside of Z, and you look at the W point, then it's going to be open in the new topology. And then once, so you reduce the knowledge, so to speak, to the risky opens, and on the Zariski open, open and in particular affine, I apologize. So then, you say that if U now is in AN, then the topology here, this is going to be open in Wn. So once you have those two things, it defines the topology here. But we call it strong topology here. And now, by what I explained before, the Frobenius, no, I mean, for moduli functor here, the Frobenius is defined on this set, which is now no longer a set, but which is a topological space. Because we explained that a W point is the same as a connection, blah, blah. And then we explained that the Frobenius pullback exists. So the Frobenius pullback, which I had denoted like this earlier on, respects this set as a topological space. No, respects this set, I apologize. So, as a set. Now, the theorem which underlies those two theorems there, which are of arithmetic nature, comes purely from the topology here, and then some little work, because the proposition here, or if you like the theorem, can be divided into two parts. The first part is that in this strong topology, then Frobenius inverse has the property that it is continuous. Now you can say not such a big deal, right? So the way it was defined, it's a local Frobenius. It's really a map of schemes. The strong topology should be compatible with the scheme structure. I mean, the topology on the scheme, so no big deal. So it's not a big deal. But the second thing, which is not hard, but it's also open. So it's continuous and open. That is a tiny bit more subtle to compute. And then you use in the computation precisely this formulation we had because the Cartier inverse functor, this one you understand more. I mean, it has more history, maybe you could say like this. The P in question, it's open. So you are reduced to compute on the Cartier inverse functor. And so I don't do that clearly in the little minutes we have together. So it's open. So what is the conclusion of that? The moment it is continuous and open, on a topological space, if you have the W point now of a zero-dimensional component, is going to send it to another one. So do we have an eraser here? So maybe just for the clue here. So the Frobenius pullback on M de RAM W necessarily permutes the zero-dimensional points. I mean, the W points, as I said, a K point which is isolated is associated to a single W point, so it's going to permute them.
But how do you know that you cannot have an isolated point in the set?
Well, let me write down, permute them, period, and now...
No, but if it is, there is a condition in the zero-dimensional in the schematic sense, but you can have maybe a higher dimension situation with a higher dimensional.
Yeah, but it's fine. It's fine. It doesn't happen because of this topology. So that's the base of the proof, and then you have to go on in the thing. So now Hofer is asking. I could have an isolated point. An isolated point in this topology, which is not a Zariski isolated point. I think this is your question, but it cannot happen.
Complex is like a curve which has a real point, but nearby there is no real point, but there are complex points like x squared plus y squared. You're looking.
But that doesn't happen for this topology. That doesn't happen for this topology. Once you have a point, then you have a Zariski open of points.
If the variety is smooth. But if you have a singular space and you assume that you have a point where a K point or W.
Yeah, I understand. Okay, so I understand. So because of Hofer and I haven't thought, let me add in addition here that the point is smooth on the moduli, and I will think of your question for the lecture. Okay, so that's all I had to say.
There were a lot of questions. Are there more questions or comments? Yeah.
So could I ask, just to get oriented, so if you view this theorem as a formal scheme over W, is it not true that F full-width can be upgraded to a morphism of formal schemes? Not just on W points, but literally.
No, the MW was on the formal scheme here.
Right. So is it not true that F fullback can be upgraded?
No. I apologize. I put a hat on the scheme. I didn't put on the moduli, and I apologize. This is you look at the F we use. Because you want a fixed point, and so you want, let's say, an isocrystal. So on the isocrystal should be a formal connection.
Right, but all I meant is that is it true that, I mean, you talked about F pullback being a map of W points, but is it true that there's also a map of formal schemes?
No, I don't say that. I don't know. I would like to know, but I don't know. I just talk on W. I can only talk on W points, and why can I only? So it's a question. In fact, I'm fighting with since 1 year. Once I had discovered with Johan that there is a proof, direct proof, not going modulo P, using but more complicated tools. You can argue on W points. But you cannot argue on the scheme itself. I'm not claiming that the Frobenius asks on the scheme. Maybe it does, but I cannot prove it. So, because if you look at the scheme which is defined over, because the one which is given is the one over capital K. On the scheme over capital K, you have K points which do not extend as W points. And those, I have no ID. So I have to exclude them. Because I don't know that the Frobenius is asking on connections. The only way I can make it act on connection is if I have a W model. So, and even really W, non-ramified. Even if I knew I have an integral model which is ramified, I could not make the Frobenius act on it.
I was only hoping for action on a formal scheme. So I wouldn't, I mean, if I just look at formal scheme, then there are no K points, which...
This is true, yeah. But yeah, maybe. Thank you for the question. But in the present state of knowledge, I don't know, which is not to say doesn't. So now, if you look at as you say, the moment, yeah, that would mean you take the formal scheme, but you take ramified points. That I don't know. Because the formal scheme is recognized by looking at all ramified points. In fact, but that I don't know. I can only make this Frobenius pullback in a non-ramified situation. Because the radius of convergence of the exponential function is what it is. And this is the way, which is the reason why the Frobenius is well defined. That means does not depend on the choice of the Frobenius lift on the scheme, is because you take another Frobenius, you look at the two expressions it gives, that gives you a Taylor expansion, and this Taylor expansion is like an exponential function, and the radius of convergence is 1, and I cannot make it better than this.
Yes, Fisher?
So I have a question. So a natural thing to do would be to go beyond Fontaine-Laffaille theory now with modeling techniques like prismatics. Yeah. So, in fact, last year I was thinking, but that this proof is, as I said, part of the knowledge was already available, but part is new. And okay, this method gives what it gives. I don't think it gives, so prismatic, what I believe, because at least if we believe in Simpson, we can believe that not only those objects which are rigid underlie an F-isocrystal structure and then more crystalline structure on the Fontaine-Laffaille module, but it should also be, as you suggest, a prismatic crystal, at least for P large. And I started thinking of this, and I also asked Bhargav, in fact 2 or 3 times, what does that mean, a prismatic isocrystal? Because here, when you come from C, all you could see is the isocrystal, because it comes, the information is coming from C, so it's iso, it's on the field. So there was a long discussion. Finally, I think those Japanese, the young Kato in Hanoi, there was a young Kato and someone else giving a lecture. So their notion of isocrystal is you divide by I, the ideal of the prism. So it seems to be fixed now. I asked them whether it's really a definition which is fixed. But once you do that, then their new theorem with those groups of people identifies the crystal and the isocrystal with this definition. They can always live from crystalline representation to those. So in a way, they do the work for us, so to speak. So I think upgrading to prismatic, it would be very nice to have a way to upgrade to prismatic directly out of the algebra. But in principle, this upgrading to prismatic properties should be already available in the literature by what they prove, that once you have a crystalline p-adic local system, maybe non-ramified, I don't know, I don't even know what it means when it's ramified. Once you have that, then you have prismatic theorem object, so to speak, which underlies the situation. That is what Bhargav and Peter proved on a point, and now they have a generalization in the smooth situation here.
Thank you. Maybe we should keep further questions for the break. So thank you, Hélène, and we resume at 1:15.